Okay, I'm going to walk you through quiz 13D. This is a pretty cool problem, so I thought it would be fun to share it with everyone. An elevator is accelerating downwards at 2 meters per second squared on Earth. The occupant of the elevator has a mass of 60 kilograms. She's holding a suitcase in her hand that has a mass of 10 kilograms. So let's visualize that. Person, suitcase, elevator accelerating downwards. It doesn't matter if it's moving upwards or moving downwards. It just matters that it's accelerating downwards. One thing that's not important is this angle here. And I know that's not 100% clear to some people from the wording of the prompt. If I was going to use this quiz again in the future, I would rewrite it to make it a little bit more clear. But I wanted you to visualize it as straight up and down. We don't need the extra difficulty of a diagonal pull. So let's move on and find the force that exists between the occupant and the suitcase. Okay, now it's definitely time to pause and make a force diagram. The suitcase has a gravity force, and it's being pulled upwards by a person. You could call that tension or normal. I'm going to choose to call it normal. From the fact that it's accelerating downwards, I know this gravity force is bigger than the normal force, and those are the forces on the suitcase. Maybe in a minute I need to go do a force diagram for the occupant. I hope not. That sounds complicated. So let's just study the suitcase and see if that's good enough to get an answer for the force between the occupant and the suitcase. Well, if we're studying just the suitcase, then the acceleration of the case, net force on case, mass of just the case. I kind of want to make a just in case pun, but I'll spare you. Looks like it's a normal force plus a gravity force. And the mass was given as 10 kilograms. In this case, the acceleration is downwards, so negative 2 meters per second squared. Normal force is unknown, that's what we're trying to learn. 10 newtons per kilogram times the mass of the suitcase. And again, the gravity force is downwards, so I'm going to squish a negative sign in there. Notice I don't squish the negative sign in front of the symbol. I let the symbol stand for a negative number or a positive number based on the drawing. I'm kind of hoping that physics is going to tell me that this is an upwards force. If it doesn't, if it gives me a negative sign when I solve for this, I'm going to worry a little bit. So this in here is ugly and messy, and I'm going to leave it. Well, actually, no, I can simplify it right now. 10 newtons per kilogram times 10 kilograms is 100 newtons. Multiply both sides by 10 kilograms, because who likes denominators? So negative 20 kilogram meters per second squared, equivalent to newtons. Oh, I love it. Now I can add 100 newtons to both sides, which is great. The units are alike. Positive 100 newtons plus negative 20 newtons. I've got a normal force of 80 newtons. The person is pulling up, but they're pulling up with a force that's a little less than the 100 newtons of gravity force, or a little less than the weight of the suitcase. What this would feel like to you if you're in the elevator is, my suitcase is a little lighter. How interesting. There's part A. Part B. If the occupant was standing on a scale, what would the scale read? And it's bolded in kilograms. Wow, a scale that reads in kilograms. Funny, the scales in the physics classroom all read forces, and they read forces in newtons. I'm going to think about that later. But they're standing on a scale, and it's the occupant, so now I have to turn to studying just the occupant. Now at this point, y'all, you can choose to study just the occupant, or you can choose to study the occupant plus the suitcase. Either choice will get you to right answers. You can make a different choice than me and be consistent and be perfectly fine. So I'm going to choose to study just the occupant. Since it's just the occupant, I'm going to use 60 kilograms. That was given up here in the text. Now, I haven't made a force diagram yet, so I'm going to do that over here. We know that the person pulled down the suitcase up 80 newtons. Therefore, the suitcase pulls on the person on P by S with negative 80 newtons. We know the person has a 60 kilogram mass. By now, I hope you'll forgive me if I just cheat and write that as negative 600 newtons of gravity force on person by Earth. If you have to show it, it's 10 newtons per kilogram times 60 kilograms. And then we have an upwards force, and it's a normal force by whatever they're standing on. And it says they're standing on a scale, on person by scale. So this is between the person and the scale. I bet that's related to what the scale is reading, so I'm interested in that. This is known, and this is known, so I feel ready to return to my equation and say that the F net, which is this plus this plus this, I'll squish in here scale. This is the normal force on the person by the scale, gravity force, normal force by suitcase. The scale one is the only upwards one. Gravity force was 600 newtons down. Suitcase force was 80 newtons up on the suitcase, therefore it's 80 newtons down on the person, just by force pairs or Newton's third law. Multiply both sides by the denominator. It's going to come out to 120 kilogram meters per second squared, because it's negative 2 times 60 kilograms times meters per second squared. I'm multiplying by 60 kilograms, multiplying by 60 kilograms. So negative 120 kilogram meters per second squared. Now I'm going to add 680 newtons to both sides. So 680 newtons cancels off these two. Positive 680 minus 120 gives me 560. And that's the normal force on person by scale. Okay, great. 560 newtons on person by scale. I'm going to claim that clearly means 560 newtons on scale by person. Person standing on scale, scale says, hey, 560 newtons, how much is on me? The scale is designed so that if it's feeling squished by 560 newtons by the person above it or the thing above it, it's going to read a mass of what? Oh, divide both sides by 10. So it thinks you have a mass of 56 kilograms because you're accelerating downwards. You actually have a mass of 60 kilograms, given in the problem, 60 kilograms. Does it make sense that the elevator says, you seem a little lighter because we're accelerating downwards? Well, yes, and we could reason by extremes. Suppose the elevator is accelerating downwards so fast that the person is like about to lift up and fly off and bounce around inside. Oh, well, then the scale is going to feel no pressure at all and read as low as 0. So yes, it makes good sense that the weight reading goes down a little when the person is accelerating downwards. And once again, to reemphasize, if you chose to study the person plus the suitcase, you would eventually get to the exact same answer, that the scale is going to read 56 kilograms while it's accelerating downwards. So I'll give you one more look at the back, where we argued from the normal force on the person by the scale to the reading of the scale. You're not truly 56 kilograms, that's just what the scale thinks, because the scale is confused by all the acceleration. And then let you see one more time the phrasing of the question. And the answers to part A and part B. Good luck.